Hi, welcome to this video. In the previous video you learned how a fluid flows through a packed bed or through a bed of particles, and now I would like to do a simple sample calculation with you, a very simple calculation to apply this knowledge. So we have a flow through a shaft furnace. This was one of the examples from the last video. And first we will look at the given task. So what do we want to talk here about? Then we use the Ergun equation, the equation you learned, to solve this task. And then we question the given values on multiple point of views and look again at the equation. So the task is that we have a steel company, Iron Tech, and it operates a shaft furnace to reduce iron ore pellets using a stream of reducing gas, mainly CO and hydrogen, at superficial gas velocity of 0.2 meters per second. So we have iron ore pellets and we put them into a shaft furnace. They fall down. We have a stream of gas going into the other direction with a velocity of 0.2 meters. And this gas goes through the bed of particles, which is moving down. And then we have a reduction to get our iron. So the engineers at Iron Tech are tasked to optimize the gas consumption while ensuring that the bed of pellets moves smoothly through the furnace. One key design parameter is the pressure drop across the moving bed. So of course we have friction with the gas, or we have resistance from the bed, and this is why we have a pressure drop along the bed. So we are losing energy from the gas. And if the resistance is too high, the gas blower consumes excessive energy. So we really have to pump a lot of energy into the system, which we lose due to pressure drop. But if it's too low, the gas solid contact may be insufficient for proper reduction. So we need a certain flow that enough gas comes to the surface of the particle. And to estimate the pressure drop, the engineers model the ore bed. So the iron ore pellets we are throwing into the furnace are modeled with as a packed bed, which is moving. So it's a moving bed. It's a packed bed moving, not sitting. And therefore we can apply the Ergun equation because the Ergun equation works with packed beds. And we have a pellet diameter, which is 10 millimeter. It's very large, as we will see. And we have a bed porosity of 0.4, also 40%, 0.4, which is very typical for a random packed bed. We have a gas viscosity, a very typical value, and we have a gas density of 1.2 kilogram per cubic meter. Okay, with this we can take a look at the Ergun equation you remember maybe from the video, and this equation is the pressure drop per length. So we calculate, we don't have a number here of the height of the bed, so we just calculate it per length. We say 1 meter. And then we need the density of the gas, we have this. We need the velocity of the gas, we have this. The size of the pellets, we also have this. The porosity we have, and we need lambda. And lambda is the drag coefficient. So we know the drag coefficient CD as a function of Reynolds for one particle, and now we have lambda as a function of Reynolds. So this is the drag coefficient for a full bed of particles. And this equation was also given, 150 multiplied 1 minus epsilon divided by Reynolds plus 1.75. And if you look at these numbers, we mainly have everything. The only thing is missing is the Reynolds number. But the Reynolds number is something we easily can calculate. So we need the density of the gas or the fluid, the velocity, the particle size, and the viscosity, dynamic viscosity, and all these numbers are given. So 1.2 times 0.2 times 0.1 divided by 10 times 10 to the power minus 5. And if you consider all the units, we get a dimensionless number, so no units, and we get a Reynolds number of 120. So it's not laminar flow. This is why we have to use the Ergun equation, because the Ergun equation also works if we have a pressure difference in the bed, right? So this is not pure laminar flow. And now we can put these 120 Reynolds into our equation for lambda, because here's the Reynolds number, here's the epsilon, and then we get a total volume, a number for lambda, which is 2.5. So very easy. And with these 2.5, we can go back to the Ergun equation So looking again, we have all the numbers. 2.5 was calculated based on the Reynolds number. Then we have the density, we have the velocity squared, and we have 1 minus. So be careful, here is, I don't need brackets because here is a different, here's a gap between the lines. 1 minus 0.4, 0.4 to the power 3, and 0.01 meter, so 10 millimeter as size. And this is 112.5 Pascal per meter. This is a very low value, right? And we should wonder if it makes sense or not. I mean, we have a lot of assumptions and we have a very low value. And maybe we look again at the numbers here. And the task, okay, doesn't change. But if we look at the numbers, we have a gas viscosity of air and we have a gas density of air. But we don't use air, and probably this is at ambient condition, and in the furnace we don't have 25 degrees Celsius. So looking again, we can use the ideal gas relation to get the density of the fluid, and normally we have a pressure which is 1.5 times 1 atm, so 1.5 multiplied. And we also have a mean molar mass, which is a mixture of CO and hydrogen. And normally the ratio is 70 to 30. So we have to take the molar mass of this. And the temperature is around 900 degrees. And if you put all these numbers in here, so here's the pressure, kilopascal, 150 kilopascal, 1.5, right? 0.02 kilogram per mole for the molar mass. We have the gas constant and the temperature in Kelvin, and then we get an even much lower density, which makes sense at these high temperatures. So now we have a density of 0.31. And there is also a possibility to calculate the viscosity. It's the Sutherland's law, and then we would get a slightly higher viscosity of 3.85, 10 to the power minus 5 Pascal. So a little bit higher viscosity, much lower density. If we put these values again, we get a much lower Reynolds number. Reynolds number now is 15, so we're getting close to the laminar area. And if we put these numbers into lambda, we get a slightly higher lambda. This change, sorry, here is the wrong number, but the calculation is correct. So this number should be 15.8. And if we then put our 7.5, which is the new lambda, into the equation here with the new density, then we will get an even lower pressure drop per meter. And okay, the bed normally is a few meters long, so we have to multiply it by 5, 6, 7, but we are also still not in the kilopascal range, so we have a very low pressure drop, but we have extreme large particles. 10 millimeter is very large for these kind of particles. And these kind of large particles don't have a high pressure drop. But if we would decrease the particle size by 10, so from 10 millimeter to 1 millimeter, so we would have 0.001. It's a square dependency in the Reynolds and the Ergun equation. And this means that the pressure drop would increase by 100. So we are not that bad. We have a very small number here for our example because we have very large particles. But if we would decrease the particle size, the pressure drop would increase dramatically because of 1 divided by d square, which is a little bit hidden here because we also have it in the lambda via the Reynolds number. There's again d, so but it's a d square dependency, and therefore this very low value makes sense in this example. And with this, we looked at the task with working with quite large particles, giving a large pressure drop. We just applied the Ergun equation as you learned from the video. And then we thought about the numbers. Does it make sense for 900 degrees and the density and viscosity, and also if or why the pressure drop is so small. And with this, I would like to thank you for watching the video. And if you have any questions, just let me know.